Hello everyone. Today I, Aditya Niranjan from the batch EB15 third year Bennett University, will be talking about Introduction to Finite Automata. And in this video, we'll be covering mostly DFA, that is Deterministic Finite Automata, and also we'll be taking a glimpse of representation of automata. So now coming to alphabets. An alphabet is any finite set of symbols. Example, ASCII code 01 binary alphabets. So it can be anything basically 01 and the alphabets ABC or extended just depending upon the language. Strings. The set of strings over an alphabet. So this is the symbol of the string. Let me just point it out. So basically this is the symbol of string and is the set of list, each element of which is the member of string. String shown with no comma, example ABC. So basically this symbol denotes the set of strings and this symbol stands for the empty string. Now we'll be seeing the example of strings. So this is a basic example of strings. That is 010001. Now we'll be looking for languages. A language is a subset of strings for some alphabet. Example, the set of strings of zeros and ones with no two consecutive ones. So this is the language of the above mentioned zeros and ones with no consecutive ones. Now deterministic DFA, basically deterministic finite automata, a formalism for defining languages consisting of Q, which basically represents the finite set of states. This symbol, that is sigma, typically represents the input alphabet. This symbol represents the time transition function, and Q naught in Q. Basically, this Q naught is the starting state or start state, and F, that is total the set of final states, and this means that final states is always a set of the total number of states, that is final states. The transition function takes two arguments, a state and an input symbol. So basically this is a transition function which is taking a input, basically state and an input. The state that DFA goes when it is in state Q and input A is received. So graph representation of DFA. Basically it's a nodes which is equal to states. Arcs represent the transition function. Arc from state P to Q labeled by all those input symbols that are transition from P to Q. Arrow labeled start to start state, final state indicates by double circles. So it says the basic in how to represent DFA. Basically final states have double circle and arrow labeled start to start state. This is an example of a graph. So this is the starting state, as we all can see. This it is as well double circle, so it's a final state. This B, which is another state, which is also a final state. The arrow representing the start from one state on particular input to the end. So if it's on A and if the input is 1, then it will be going from A to B, and if the input is 0, then again it's just going back to A, as we all can see. And C is not a final state, so at here basically this is for the all the strings without two consecutive ways. So we can see if once one has come, the other time one has come, it will end up on a state which won't be going on a final state. So from here, if it's again 0 and 1, so it will be again repeating on C itself. And if it's a single one, it will be going to final state. If it's single one, then again 0, then again final state, and again if there is a not consecutive one, then again it will be rotating to final states. So this is alternative representation transition table. So this is the final states A, B, which are final states, and this C, which is not a final state. So on a particular input where it is going, it shows the table. Now we'll be just seeing a testing membership. So basically in this, as we can see, as 0 is coming, so it's in a start. See, basically this is the current state, which that is the start state. So as soon as 0 comes, it will be again rotating to A itself, as we can see with the array. See, it has rotated. So now the next symbol which is going to come is 1. So now it's currently on A. So when 1 comes, it will be going from A to B, as we'll be seeing in the slide. See, it has shifted to B. Now again the next symbol is 0. So now from B on 0, it again goes on A. That will be seen in the next slide. See, from here, the next symbol is 1. So again it will be going on B. And again, then it's 1. So again it will be going on C. And from C it won't go anywhere because there's a loop, and this is the not the final state, it's some dead end state. So now there's no other thing, so it will be staying on C itself. So this is an example which is the machine accepts a string if the process ends in a double circle as well. See. So now let's practice some of the questions. So according to this question, it asks us to build a DFA that accepts the set of all strings over 0, 1 that end with 00, as we have seen. So basically, let's see how to do it. So let's suppose this is the start state. This is basically, let's consider it as Q naught. So from here, if it is coming 00, so you'll be taking directly, see, basically, let me just mark it. See, this is the start state, it's coming. If there are two zeros, double zeros, then it will be proceeding forward. So 1 0, the other 0. This will lead to final state as we get it. I mean, see, it's ending with two zeros. There are two zeros, it's ending with 0. So here is the final state. We are able to find the final state. Now for all the other cases, so it's on the initial state. Let's consider it as Q naught. Okay. So on Q naught, when 1 is coming, it will be again coming back to Q naught. As after 1 again 2 zeros came, then it will be going to the final state. If 1 0 came, and then after 1 0, if there is any 1, so we'll be again transferring it to Q naught, because we need two zeros compulsorily to the string to be accepted. So again we'll be shifting to Q naught, and if after that two zeros came, then it will be going to final state. After Q1, so in this case 0 has came, and again in the similar way, if 1 is coming, then again we'll be shifting. In any case, if 1 is coming, we are shifting to Q naught because we need two zeros at the end. So that is only possible from Q naught that we can get two zeros, which we need to the final state. Let's make this Q2. And after reaching to Q2, if there are any number of zeros, obviously at the end it will be 0 0 0 whatsoever, and it will be going in final state. So let's see another question. So it says draw a minimal DFA which accepts the same language as a DFA with alphabet A and B is given below. So this is not a minimal DFA. We need to convert it into minimal DFA. So how we can convert it? So let's just first understand the question. So basically, this is the starting state. Okay. So if A is coming, it's going to final state, directly going to final state. A is coming, if this basically string is starting with A, it's going directly to the final state. Okay, no problem. If the string is being started with B and then A is coming, it's going to the final state. After B, A is coming, then again to going to final state. Okay, great. And in this case, if after B, B is coming, means two consecutive B's, then it will be going to dead state, basically dead state. If two consecutive B, so B, A, no problem. Here A is coming directly, then again directly going to final state. Okay. So let's just try to make it. So basically, if B is coming, okay. So let's just try to make it, and let me just show you and explain with you directly with the solution. Okay, before going to the solution, just try to figure out some of the things as we have seen in the previous slide that basically all the inputs are taken if the string is starting with the alphabet A or the string is having the second alphabet as A. So these two are the final states. Okay. So is it possible how we can minimize it? So let's just see. If A is coming here, if we can just directly turn this as A, will it make a minimal DFA? I mean, let's just see for the all the values. So basically here A is coming directly, okay, no problem. If after B it was going, A is coming, then it was going to the state T. And again now A is coming, it is going to the state S, and both are same. A and B are again coming, then it's same. So we can say it is, now we got one of the minimal DFA. Okay, so is there any more way to again shorten it down into more smaller? So let's just figure out. A, okay, after, no, we can't see any other way. So just directly just skip to the solution and let's see we got the right solution or is there any other way. Okay, we got the right solution as we see here. The minimal DFA is the same one as we came up with. So basically this and this are both same and this is one is the minimal one. Basically both takes the same kind of input and results in a same solution, but this one is the one which we, this one is the minimal one and this one was a bit which was having extra state, we can say like that. So we figure out the minimal DFA. So let's get forward to the next question. So this question is about the number of states. So number of states. So definition of a language with alphabet A is given as following. So language is given as L equal to A to power n k, where k is greater than 0 and n is a positive integer constant. What is the minimum number of states needed in DFA to recognize L? So if you are not able to understand the question, so let me just make it let me just read it once again so it becomes more clear to you, and later on I'll explain the question. Definition of a language L with alphabet A is given as following. So this is the definition of language with the alphabet L given here. So L equal to A to power n k. So L is given as A to power n k, where n is a positive integer constant. So n can be anything from 1 to infinity basically. This is as it is a positive integer constant and k is greater than 0. So same goes with for k, that is a positive integer constant. What is the minimum number of states needed in DFA to recognize L? So this can be solved by taking an example. So let's take a particular value for n and k. So here in the example they have taken as n equal to 3 and k equal to 1. Okay, so language will be a to power, language will be a to power 3 into 1, that is a to power 3, that are 3 a's. So in the state q naught, if a is coming, okay, no problem, it is going to the next state. Again a is coming, no problem, again it's going to the next state. Again if a is coming, it's going to the final state. So in this way, if after this, it means basically in the language the number of a should be thrice, basically it should be 3 times. So in this, see, as we see here there are 3 a's, so it's accepting multiple of 3, basically a should be the multiple of a. So again after this, if a is coming, see 1 2 3, again it gets accepted. So accordingly this question has been given. So if we count the total number of states, which is 1 2 3 4, that is n plus 1. and in this way we get the solution, that is n plus 1, or it can be also given as n plus k, as we took the value of k is 1, but it doesn't say that k is a positive integer constant. So in this way we get our answer. So by this I'll be ending my presentation, and I hope everyone must have understood about the basics of DFA and will be able to solve some of the basic questions. So thank you for watching this video.